So as you know that San Diego presents a tremendous opportunity in anything health sciences, in anything biotech. And, uh, one is the genomics, those aspects of biotech, the drug discoveries, our, various health sciences department, our bioengineering department, and so on. But one of the things that this kind of community can contribute tremendously is also from a digital health perspective, right? And so, about 3 years back, with a workshop where we brought together thought leaders from various different companies uh, and also healthcare providers, we launched the Connected Health Program. And we now have about 5 different projects going on in the Connected Health Program. One of the things that you'll see is that CWC cannot fund everything fully, but what we try to do our best is seed things and encourage our PIs to apply to various kinds of opportunities, NSF, NIH, and so on. And so, faculty like Drew Hall, who is here, Patrick, who give a talk. So they have been very, very successful. And I'm just pointing out them because, so their work is on the sensors, RF, wireless side. And, and we have been also successful, besides that sensor, RF, wireless, also been quite successful in the last, I would say about 4 or 5 years in getting large grants from NSF and NIH. And there's a program called Smart and Connected Health Program, and we have been fortunate to get 2 grants from that. It's a very, very competitive program, and the latest grant we got is a $2.5 million grant in to study ASD and use essentially wireless technologies for ASD guidance, ASD training. So wanted to so we have multiple projects going on. Wanted to highlight 2 projects from that. I think that one of the legacies of wireless, if we look back 50 years, I think will be about how it will transform health. And it's just we are at the very, very beginning of that transformation. So we are quite excited, being UCSD, being San Diego, to be leading in that effort in digital health, connected health. And I think that with Scripps, many of you might know Scripps Translational Institute. So it's right there at the backyard. They are leaders in digital health. We are working with them. We are working with Teradata, um, who is also here, our partner, and we're also working with Samsung Digital Health, and also Kaiser. I shouldn't forget. So with those partners, I think we are doing quite well in jumping up, sort of jump starting this connected health program. I wanted to spend the next, let's say, about 15 minutes to talk about this particular this particular research. And one of the reasons being that 2 years back, when we were formulating our projects, we had the hope that we can take this kind of research to actual clinical trials or clinical studies. And after a lot of roadblocks and a lot of logistical challenges, we have been able to. So I'd like to present that aspect to you. Uh, as you saw in the STIP, or the connected vehicle research project, where we are building a system, and there's a lot of hardware and software. Here also there's a large systems aspect, but it also involves patients, real patients, and there's a lot of learning that we are having from those real patients, how IoTs should work and should not work. When patients are actually getting out of our study and saying enough is enough, I don't want to participate, and when patients are actually embracing our study and saying that yes, this is something that is that is changing my life. So not all those learnings are documented here, because we have to still go through a certain kind of understanding of how we publish those. But I'll show you some snippets of what we are already learning. So this is about using IoMTs, things that Drew and Patrick and all others create and are creating. Uh, IoMTs, Internet of Medical Things, and machine learning, how to enable personalized chronic care and predictive chronic care for patients. In this particular work, we have been focusing on blood pressure. So on pre-hypertensive patients. I wanted to, I don't know why it's not moving. Should I point to something? It was working fine. I can go there also. So as he's so wanted to acknowledge Pohan Chiang and Jared for the PhD students for this work, and Dr. Lee and Dr. Wang from UC San Diego Health. Okay. So we started, as I said, we started this work about 2 years back. We started the work with Fitbit, and our overall idea was that we will create a system which is constantly monitoring, and we need to find a better word for monitoring, because sometimes monitoring is not acceptable to a lot of users. But essentially, we are collecting data. We are collecting vital data, behavioral data, and contextual data, and this is going on all the time. And then using that data, we are essentially trying to do two things. One is that uh, we want to predict some target variables, in this case blood pressure, but this framework can be used for any other chronic condition. uh, and we also want to figure out what might be the important features that are contributing to your blood pressure. Why is that important? So this is my personal story. For various reasons, I ended up being pre-hypertensive to sort of borderline hypertensive. And my doctor asked me, and if the same experience you have had, or that is, you have become hypertensive or pre-hypertensive, where your doctor is figuring out, instead of putting you on medication, what to do, essentially you will see that the doctor recommends various kinds of things that you should do. Exercise well, sleep early, get more potassium, do less salt, like a whole bunch of things. And I tried my best, and I reminded myself that, okay, from now on I'll start becoming more like a saint, right? And I was doing it, but at some point I started giving up one after the other.
You live like a saint compared to some of us.
I started giving up. I wanted to live a life also, but started doing some experiments as to, okay, if I do this, is it going to increase my blood pressure? If I start, reducing my potassium, is it going to increase my blood pressure? I was playing with it, but I couldn't figure out, because there was too much data. I was collecting actually a lot of data, but I couldn't figure out. And I told myself that, if I knew that I had to do this one or two things, I would have faithfully executed it. If I have to do 10 different things and completely transform my life, I would not do it. So that motivated me and my colleagues to start looking at this. So what we are trying to figure out is, what are those one or two things that might be affecting your blood pressure level? Because if I can give you that input, then maybe you can change, and your blood pressure might be under control. There are many other reasons for increasing your blood pressure, but lifestyle is a huge, huge contributing factor. So that's what we are trying to do here. Now, so with the Fitbit, we were very encouraged, because so this was not a patient population, this was volunteers, and with that population, we could get to a very, very good accuracy levels, creating a model and predicting what the blood pressure might be, vis-a-vis what your lifestyle factors are. Then we thought that, okay, we are now ready to launch a clinical study. And so while it took us quite some time, we eventually were able to go through all the different wrinkles and do a clinical study with the help of UC San Diego Health and ACTRI. And that study started, I think, about 6 months back, and is continuing. Uh, by this time, we are supposed to get to 90 patients, but we are crawling. We are not being able to run. We are crawling, and we are now up to 34 subjects. And as I said, so we had, the good thing is that there are doctors in our team and ACTI in our team. So we figured out that we'll have very diverse demographics. We'll recruit people whose blood pressure is below 140/90, that is pre-hypertensive to borderline hypertensive, because we did not want anyone in the study who is already on medication, because that's another different kind of, totally different league by itself, in terms of understanding what the implications are. And we switched from Fitbit to Samsung Galaxy Watch. And I have to say that we couldn't have done that without a very, very active support, participation, collaboration from Samsung. Samsung has been a great partner. We have gone through all kinds of, maybe the Galaxy Watch, it, it has already been used in some clinical studies, but maybe we have been stressing it in various different ways. So whatever has broken, whatever APIs from the cloud to the Samsung Watch, the Samsung engineering team, both here as well as in Korea, have been, very, very supportive of us and very, very responsive. So thanks for that. Uh, with the Samsung Watch, and there's a reason we chose the Samsung Watch, because the Samsung Watch also gives us the PPG signal. And the PPG signal is a very interesting signal. It can unlock various other indicators, and I'll mention that later. And so the lifestyle data that we have been collecting have any of you been using Samsung Galaxy Watch? Fitbit? Fitbit? Okay, so a few for Fitbit, none for Samsung Galaxy Watch. So we have to do a lot of evangelism with this crowd, right? In terms of adoption. Apple Watch? Okay, a few Apple Watches, okay. I saw a Nokia hand go up on Apple, wondering what's going on there. Okay, so any of these watches actually can sort of point out your heart rate zone. So at any given time, you can figure out whether your heart rate is at a mild rate, at a medium rate, or at a high rate. Okay. Similarly, your resting heart rate, your maximum heart rate, number of steps, walking, running distance, walking, running speed, sleep state, sleep duration, bedtime, wake up time, and so on and so forth. We have listed a few. And so what we did was we ported the model that we had created with Fitbit to real patient data and to these different parameters. And I have not gone into the details of the machine learning model because I thought that would not be interesting. And if you wanted to, you can look at our publication. Actually, this is the first publication, and then there is a second publication which I'll talk about. Yeah. However, what we saw is that as we are trying to fit our model to the patient data, and Pohan, correct me if I'm wrong or exaggerating, we faced a lot of obstacles. The patient data was quite different from the volunteer data we had collected. We have honestly not yet been data scientists in trying to sort of take a microscope and figure out everything about data, but the data that we have collected, it's a trove of well that we'll hope to understand why the patient data was, it has so much more fluctuation, for instance, than the real data, the volunteer data. But we came to through multiple iterations, came to an MAE of 5.7 and 3.9, which is very much within the range of medical devices for those of you who deal with medical devices. So for instance, your blood pressure meter that you use, you'll see that it has a ±5 error rating. So this is pretty good in terms of the error rating. So using this Samsung watch and the BP Omron, we were collecting the vitals data, and then we are mixing up with the lifestyle data, the contextual data, the demographics data, male, female, age, so there are various kinds of data that is, available through our studies. So this study, as you understand, is live patient study, right? Not like, you are going to a county and looking at a database and getting data from there. This is live patient study, and so it had various interesting implications. So essentially what we are doing is we are collecting data, 3 months, we are collecting data from each individual, and then we'll go back to them saying that this is what, this is a report on you, a personalized report on you, including recommendations of what you may want to do to reverse trends. So for instance, if a patient's trend is that the blood pressure level is flat or going high, then what to do to reverse that trend. So let us look at how we want to identify what might be the top factors that might be responsible for your blood pressure. And my top factors will be very different from, for instance, Mark's top factors versus Drew's top factors. So that's one revelation that we already had. And it was borne out again by the patient's study that we are conducting. So what we did was we looked at various different kinds of ways of figuring out what would be your top features. I skipped one detail, and that is the model that we had created was a random forest-based model. And in that random forest model, what we can do is, those of you who know random forest, there are the features. You can start with any feature, and you typically start with features, building the random forest feature or random tree with features which will give you the most effect in terms of the accuracy, and so or the prediction. And because we don't know when we start with, we create hundreds of random trees, and that's why we say random forest. So those features which improves the prediction of the blood pressure most, those features we can potentially consider as the most, as the top factors or the top features for your blood pressure. So for instance, here, I don't know whether you can read them. This says the top feature for this individual is the time at which the blood pressure is being measured. And then the next one is the heart rate. The next one is the number of steps in the last 1 day. The next one is maximum heart rate in the last 48 hours, and so on and so forth. Okay, so we can get to see by exploring the random forest, what features are the top features. Similarly, my student Pohan, he discovered that Shapley is also a very interesting way of uncovering, what features are the most important features. That means in the case of Shapley, if this is the median value, uh, the these features X, the ones that contribute most positively or most negatively to the prediction from the average, we can consider them as the most important features. But if you look at by the definition, interestingly, and we see this for patient by patient, the RF based features, the random forest based features, and the Shapley based feature importance coincide very, very accurately, very coincidentally, and very accurately. I shouldn't say coincidentally if it is borne out by patient after patient. So that's an interesting discovery. Whereas this Pearson correlation heat map, it's also an interesting heat map, and we have trimmed down various features so that we can fit in here. But this shows linear relationship. The red, the more positive, the darker blue, the more negative, and anything light means that there is no correlation. So the Pearson correlation and the mutual information, these are also other ways, and those don't show as much relation as or as much similarity as RF based feature importance and Shapley values do. We still don't know. So we are figuring out these feature importances from various different sources. What we still don't know is that how to mix it up. So there's an active study we are doing. However, for the patient population, because we wanted to get back to them quickly, what we are doing is we are taking a mean of all these, whichever features are important, the importance of the features, we are taking a mean of all these correlation, ways of finding the relations and determining these are the top features for this particular patient. However, we are trying out various different other ways. So we go back to them saying that, actually I'll skip this and show you. So this is a report. This is an actual report to each particular patient, that your average blood pressure level is this, systolic and diastolic. The lowest is this, the highest is this. And then we say that based on your blood pressure and lifestyle data, our analysis shows your blood pressure has the greatest correlation with the following, and whatever those factors are, right? We just let them know, and we don't ask them to do anything. We just let them know and continue to monitor what they do, because we want to understand, will they be motivated to change their lifestyle? Will that change in lifestyle do anything to their blood pressure levels? That's what we want to do. And these are graphics which are showing these factors, the most important factors, how they seem to be related to their blood pressure level. So in this case, the feedback we have given is number of steps and average walking running speed. That these are your top two factors for this particular patient. And what we see 20 days, because this is an active study going on, right? So 20 days after that feedback was given, so that feedback was given on this day, and so now we are monitoring on this day. This is a few days before this, event. What we see is that indeed this particular patient has increased his or her daily number of steps from this to this. It's quite a bit of increase, right? Not coincident. He or she is trying to increase the number of steps to follow the feedback, and the walking running speed has been also pretty significantly increased. So what is the effect of that increase? So what we have plotted here is the diastolic and the systolic values over the first trial period, that is the first 90 days of observation. And what you see, so this is a linear trend. So we are plotting the trend of diastolic and systolic, and we could have used various functions, but we are using a linear function. And so the important thing is watching this number here. So this is like going a little positive. What that means is the blood pressure during the study was going up, the diastolic, and the systolic was pretty much remaining the same, just going a little down. Whereas after the feedback, and there was a break, as you see, after the feedback, uh, as you see visually, the trend, and if you talk to a doctor, everything is about trend lines. So the trend line is now negative, which is very good, right? The blood pressure level is going down. The diastolic is going down. You see from positive 16.016 to negative 0.1215. And also here, it's pretty flat and it's going down a little bit, the systolic. So this is just initial results, just some initial positive results, encouraging results though, because what it shows is, without us telling, do this or do that, we are just giving feedback. There's a reason that we couldn't also tell them what to do, because then that clinical trial would have created a major IRB review. So so essentially we designed the IRB approval in the following way, that we'll not actively tell the patient to do this or do that. We'll just provide information, results of the study. So just with the results of the study, they are taking actions, they are reducing, or they are acting on the important factors, and the trend lines seem to be going better. So if you look at this for different patients, we have just highlighted 9 patients here. For different patients, the top factors are quite different. For this patient, it's HR zone and speed. For this patient, it's bedtime and wake up time and ratio of deep sleep stage, and so on and so forth. So so we are encouraged, and we are hoping that in the next 3 months we'll learn much more. We'll have a pretty healthy population of about 60 people and understand the effect of what we are trying to do. That is, we are trying to affect their lifestyle and keep them off medication. That's the whole purpose. Now, one of the things I very briefly mentioned is that one of the things that hampers our study and the data science part of it is that while with the variables and the sensors, you can collect a lot of data at a very low granularity. The problem is that there are some other inputs like blood pressure. Blood pressure today is very manual. You have to remember to take your blood pressure. Yes, it's transmitted wirelessly, but who cares? But the problem is that it's not automatic. You have to keep taking it. And we see in the data, sometimes people forget taking it. Sometimes people take it 6 times. Sometimes people don't take it 8 times. So there's a lot of problems with the data itself, but also with adoption, right? So what we are trying to do, remember that PPG sensor that I mentioned in the Galaxy Watch. Using that PPG sensor data, we are trying to estimate blood pressure, because PPG is taking every almost millisecond, multiple times a second. So if we can imagine using data science techniques, machine learning techniques, if we can estimate blood pressure from the PPG data, then we can have continuous blood pressure numbers. Then we don't need to rely on manual blood pressure cuff, right? So that's what we are trying to do. And I'll skip through all the details, but the good thing is that there's a data set called Mimic data set, which is for patients in ICUs, and they have collected simultaneous data of PPG signals and blood pressure levels at that time. And using that data, we have been able to create a model which can estimate blood pressure at very, very high accuracy levels. So this is like, only 3.43 mean absolute error, which is very good. And so, now the question is that imagine that people are using our system. We want to create a system where people just take a few readings using their manual blood pressure, and then after that everything is automated. So you don't need to use your blood pressure cuff anymore at all. Everything will be automated. You'll be free of blood pressure cuff. That's what we are trying to do. So we have resorted to transfer learning. Why? Because we want the real world patient to just take a few readings and not like in mimic data set. See, the mimic data set is where there is like months and months of data, and every PPG data is associated with the blood pressure reading. Whereas here, what we'll have is just a few blood pressure readings. So how can we extrapolate from that? So what we are trying to do is create the model that we have created from the mimic data set. We are now trying to transfer that to each individual through some retraining. So we are building this deep learning network. So it's a hybrid deep learning network, as you can see. Many of you can see this very quickly. It's a very hybrid deep learning network. And so after a few stages, we are actually retraining with the few data samples from the real patient, and being able to get the same levels of accuracy as if this model was created for chemotherapy. And we are not still satisfied, because we still have to get about 500 new blood pressure samples to start doing this automated way with a good, acceptable MAE. But the good thing is that using transfer learning, so suppose our target is about 5, 5 to 5.5 the MAE. So without transfer learning, we would have used 5,000 samples or needed 5,000 samples. Now we are needing only 500 samples. But our target is 500 samples is also too much, right? Telling someone to take 500 readings is just way too much. So we are trying to reduce it, and that's a struggle. Can we reduce it to just maybe 10 samples? And using 10 samples and a generic model, can we come up with this automated blood pressure estimation so that then it will feed to this bigger picture, and that is instead of using, like, let's say BP, BP manual reading with Omron, the initial readings will be manual, and then everything will be estimation based. And so it will go to our original prediction model and our feature importance model. And so this system, if you can develop, essentially will be hugely useful, because what it will do is you'll take a few readings. After that, someone is monitoring you, and only if there is a negative trend or a positive trend in blood pressure, that means your blood pressure trend line is going up, then it will tell you what to do, how to adjust your lifestyle. And of course, will be informing your medical care provider. And in case the care provider decides that no, we need to see him or her and do medication, then that becomes different, right? But this system will try to keep you off medication, but with pinpointed guidance only when needed, and will let you carry on your rest of your life, not become a saint, but just carry on leading your good life. That's the whole purpose. And I think that this is just one example of where sensing, computing, and communication can come in and really change lifestyles. So just one quick note: there's a lot to be done to make this really scalable. There's a lot to be done in terms of, because you want to collect this data anywhere you are, not when you are in a nursing home setting or in a home setting, anywhere you are, right? What that means is you are collecting data, mobile data, everywhere you are. You are in a train, you are in a bus. That's the kind of thing that we want to do. We don't want all the data to go all the way up to Amazon cloud, for instance, all the time. We want as much processing to be done at the edge. So that's why we are turning it as a hybrid edge cloud analytics framework. And in this framework, there'll be some data processing and data analytics done at the edges, some in the cloud. In the extreme case, everything will be done at the edge, but there might be compromise on accuracy. In that extreme case, what we are also considering is the cloud. You see, though we are trying to personalize, but there is a great value in community learning, right? So, what might be effective for me and what might be effective for another person, it's a matter of learning. This has been effective or this has not been. So we want the cloud to collect data about performance and figure out what is useful and what is not. And so that we can tune the recommendations more and more in a personalized way. So we are trying to build a framework which, which enables and encourages personalized learning and personalized recommendation, but without giving up on the community learning and community-based understanding of the problem. So, and to enable that, there's a whole lot of things that we are thinking of. For instance, how can we share data? Because this data is private data, right? So remember I mentioned transfer learning. How can I use each other's data? So we are talking to other colleagues to see if we can use peer-to-peer network. Maybe we don't need the cloud. Maybe it's all peer-to-peer, and maybe it can be done using blockchain. So those are different things that we are trying to explore. And eventually, if you think about it, some healthcare systems and some use cases might want everything to be done in the cloud because of various reasons. Also merging with their EMR records and so on. And some might be okay for the patients to own their data and do everything at the edge. So what we want to do is come up with a scalable architecture with service-based flexibility, flexible analytics partition. So I think this kind of thought process will lead to 6G, because in 6G, what should happen is that intelligence and our ability to understand data should be everywhere in the network, and should be done in such a flexible way, but based on the service parameters, right? So, so we think that in this kind of digital health, connected health research, we can contribute to those aspects also. I'll stop here. Any maybe one quick question? Yes.
I have a quick question. Can you go back to your blood pressure data?
Blood pressure data?
Yeah.
Like this kind of data?
No, your previous one where you're showing the declining trend. This one. There's two things that strike me as slightly odd. Before the feedback, the average blood pressure was 132. After it's 140. Yes, it's going positive, but it went up quite a bit.
No, it had gone up. See, it had gone up to about 137 or something like that. And we honestly don't know what was going on for this particular patient during this time. See, one of the things, and this data is not completely there with us, is the following. So when we see people using a device, be it Fitbit, be it Samsung Galaxy Watch, when they're just using it, they are quite motivated, and so the blood pressure tends to remain. This person was having a tendency of it going up. He or she gave up on using it because the trial period ended, and maybe it went up even further. See, that trend continuing, and we are reversing that trend.
Well, my question is actually, are the sensors we're using good enough to give you actionable data, or is there a lot of noise in the data, variability?
So that's always a good question. That question, how accurate are the variables? How accurate are the sensors? This is a question that is always asked, right? And in my discussions within the community, I feel that the day-to-day variations would not matter eventually, because the trend lines would be the most important things, right? And as I said, that if you go to any of the devices, they write at the back, if you notice, that it's a ±5 variation. So I know that, for instance, even our partner, Kaiser, has had difficulties in adopting variables because of this concern. But on the other hand, I feel that it's a little overblown concern, because even the ones that we think, take saturation levels, anything, you will see that it's rating ±1. So if your devices are within that range, I think it's compatible to the standard devices.